this video, we're going to cover circuit protection. Here's a sampling of the number of different types of fuses that have been used on the vehicle, plus one more. We're going to start off taking a look at this glass fuse. When they first started putting fuses on the car, this is the type of fuse they used. Early ones were just held in a case on a wire. They weren't organized. And then they started organizing in the fuse box. These glass ones came in different styles with some lengths and amperages. When you had one that was burned out, you could just look through that glass piece and see that the fuse element inside there was burned, and then you replace it with the same style and type that was in there, making sure your amperage rating is the same. Second type is this B one here. This is a plastic, although the early ones were a ceramic. These are what you find on the European ones. They were introduced to me as a Volkswagen style fuse, since most of the European cars sold in the United States were Volkswagens. The fuse element was not protected. The contacts were just right here at the end. They didn't make real good contact. There were several Volkswagens that I worked on that, to fix it, I just reached in there, wiggled that fuse around, and all of a sudden it started working. Then in the 70s, this style of fuse was introduced, and the entire automotive industry switched over to this style of fuse. About 20 years later, in the early 90s, this style of fuse, which is simply the same except just a smaller version of it. So in the 90s, we're now getting more and more electronic components on the car. We have a whole lot more fuses, so they made the fuse smaller. You could put more fuses into the same size fuse box. The fuse, the way that it's going to work, and you can see it best on this one right up here, this maxi fuse. You can see that there's a hole right there. These are actually soldered joints at those points right there, and that's the weak link. This one right here, it's right there in the center. That's the weak link. And it's designed when you start getting too much current flowing through there, that's going to get hot, that's going to burn open and protect the rest of the wiring. So each one of these fuses works on the same principle. And then started seeing these style, the E and F here, on Asian manufacturers, and now you'll find it on most all the vehicles, whether it's domestic, European, or Asian. I do not like these style of fuses. Down here at the bottom, you can see this is the newest of the fuses, which is essentially this one right here, but in a shortened version. Again, they're putting it into a smaller package, smaller area. You can also see that there's a metal contact right there. You can see the metal contact at those points right there. So each of these fuses has that metal contact for you to be able to go through and do your testing, and we'll talk more about that later. Here's our maxi fuse, and then went to this style of fuse, and then they just made those smaller as they went along. I put this fuse in here because I wanted you to see the difference and want to talk about the difference. Automotive fuses are classified as a slow blow fuse. By slow blow, if it's a 30 amp fuse, it can actually handle pretty close to 60 amps for a short time. If it's a 20 amp fuse, it can handle close to 40 amps again for a short time. On those style of fuses, and this is what you would find in a multimeter, those are a fast blow fuse. They're an expensive fuse. If it's rated at 10 amps, just as quickly as you exceed 10 amps, it's going to pop that fuse. It's designed to protect the electronics in the meter rather than the wires on the car. On this slide here, we're going to take a look at fusible links. This right here is a fusible link. I remember seeing the 60s, 70s, a little bit into the 80s. This would connect up to back of the alternator, to battery positive, or on the starter solenoid, which was always terrible to get to because you had the exhaust right above it. This would connect up to your hot at all times, and then this would go to the wire that fed the fuse box. And what it was designed to do is to protect those high amperage, larger wires. If you find one of these that's burnt out, when you go to replace it, you replace it with a wire that is 4 wire sizes smaller than the circuit it's protected. It's connected up to a 12 gauge wire. You're going to put a 16 gauge fusible link on there. To test these, you can take your test light, touch right there, and then you typically have to pierce through the insulation to touch on this end. So if you got a light here but no light here, fusible link is burned, needs to be replaced. Those have now all been replaced with your maxi fuses. Same thing that we're looking at here with our maxi fuses. But you can see this is 150. You'll find these 100, 120, 150 amps, maybe even 200 amps. The maxi fuse replaced the fusible link, so you're not going to find fusible links on cars that have maxi fuses. When they first started making the transitions, you might find them on those, but on the newer cars, no more fusible links, just the maxi fuses, which I like that a lot better because most of those times those fusible links were a pain to replace. To emphasize, if you do work on a car that has a fusible link, I remember this one Jeep that I was working on that came in, it was no start, diagnosed it, no power coming to the ignition system, and finally traced it back to the fusible link. Put a new fusible link on there and was waiting for the fusible link to burn. It didn't, everything was working good, so I was filling up my paperwork. I had the car running, then looked over and I saw it smoking, and then finally burns through. I checked and checked and checked. I spent 45 minutes to an hour trying to find the problem on their circuit. I could not find the problem. So I finally decided that, well, probably the person who'd worked on this before put too small fusible links. So I went to the next size larger fusible link. Man, don't ever do that. Because I had wires burned all the way along the right-hand inner fender, all the way along the firewall, through under the dash, and right to where the short circuit was. I spent about 2 more hours repairing wire on my own time. Circuit breakers. So we've already talked about this style of fuse, and I do not like this style of fuse because there's no place to test them. If you want to test these, you have to pull them out, use an ohm meter. Even looking down inside, just the way they're designed, you can't even tell if it's blown. Circuit breakers is different than the home circuit breakers. If your circuit breaker pops at home, you got to go find your box and then flip the switch to turn it back on. These are self-resetting. Once the circuit breaker cools back down inside, it'll close the contacts again. I remember one time I was driving along the freeway, and cars coming up behind me, and their headlights come on, and I paid attention. I thought, well, it's getting dusk. I should turn my headlights on. So I turned my headlights on, and watching the mirror, and his headlights go out. 30 seconds later, his headlights come back on, maybe not that long. They're on for a minute, 2 minutes, and then they shut off. And he was slowly going past me, and the whole time he's going past me, I'm watching his headlights turn on and turn off. And what would happen was he had just a little too much current flowing, and that circuit breaker would pop open. Once it would cool down, then his headlights would come back on. So that's the automotive circuit breaker. This style you'll find on the domestic cars. If the Asian or European, it's really rare to find a circuit breaker on their car, but if you do, it's generally plastic instead of metal. All right, let's watch and see what this automotive professional has to say.
When you're going to check the fuses, ideally you want to use a test light instead of a voltmeter. If you're using a voltmeter, you got to come up, touch the terminal, and then look over at the meter to see what the voltage is. With the test light, you can see that the test light comes on. As long as you get a light on both sides, everything's good. If you come up to one fuse and there's no light on either side, that fuse isn't powered, so something needs to be turned on. If you get a light on one side, no light on the other side, that's fuse that's blown. Pull the fuse out, take a look at it. You're going to look at the element inside there that burned. If it's just kind of melted back, you have something that's starting to draw a little too much current. But if you have something that looks like it's an explosion inside there, you have a direct short to ground. So by looking at the fuse, it's going to give you an idea of what kind of problem you're looking for. The other thing is, make sure that you turn the key on while you're doing it so more of the fuses are powered up.
So when it's talking about the explosion inside there, what you actually see is the solder that's inside there splatters against the walls. And if you see that, that's the direct short to ground. In this last section here, we're going to talk about different types of circuit faults. First one we're going to take a look at is an open circuit. As you look at this, you can see we have open right there. When you turn the switch on, R1 and R3 are going to work normal. R2 is not going to come on at all. This is an example of a broken wire, connection came loose, something like that. Second type is a short. Be careful of a short. When I'm talking to somebody and they tell me, oh, the problem with that is it has a short, the first thing that tells me is that person has no idea what's going on with the circuit. 3 different types of shorts. First one we're looking at here is a short to ground. When you close that switch and you can see that there's a wire that's connected over to the ground, you close that switch, it's going to pop the fuse. Short to ground, first one. Second type of short is a short to power. This one, you turn the circuit off and it stays running. When I've seen this style, where it stays running, so I had some lights that the customer's battery kept going dead and the lights would stay on. As I turned the switch on and off and watching the lights, I could see that the lights were dim when I turned the switch off, but they were still staying on. The reason is, typically when you have a short like this, it's not a really good short. It's not a real good connection. So there's some additional resistance to it. The third type of short, and that is are shorted internally. This would be like a solenoid or relay where the windings inside there are shorted. What happens on those is you have that single strand of wire that's wound around 1,000 times or so, and the insulation on there is just a spray-on insulation. So there was a Firebird that I was working on, and I don't remember what the problem was, but I traced it back to there was a solenoid up by the radiator, and that was cooling all over the place, but this solenoid was shorted internally. When the computer would turn it on, the transistor inside the computer was protected. So too much current was flowing, the transistor would turn off. I traced it back, needed a new solenoid to put that on. A couple days later, I got a phone call. So I go over and answer the phone. It's an attorney, and he's asking me, with that cooling all over the place, could that have caused the problem? I was like, oh man, did that cause the problem? I said, I don't know if that caused the problem. And so he finally rephrases the question and he says, could it have caused the problem? And so I'm thinking about it. Could coolant have got inside there, attacked that insulation, made it get soft, and then the tension on those windings pull them together? I said, yeah, it's possible. He goes, thanks. That was all he wanted. I don't know about you, but I get nervous when I'm talking to an attorney. Last one is high resistance. So I purposely made this one green down there. And the reason I did that is because you look at the negative post or the positive post and the corrosion that grows on there from the battery acid. Oftentimes it's green, and that will cause some additional resistance, and so lights won't be as bright, solenoids won't work as quickly, just get all kinds of problems. Those are our different types of circuit problems. Now we're going to take a look at a circuit. This one is a headlight circuit. So up here at the top, we have our headlight switch, 3-position switch. Turn it to the headlight, and power is going to come down here to our dimmer switch, which is going to switch it between high beam and low beam. Power side control, so power up whichever lights are low beam, whichever lights are high beam. On this one, the customer complaint is the high beam lights don't work, but the indicator light on the dash does work. What I did here was I drew it in, and if you're learning how to do wiring diagrams, one of the ways that you can teach yourself is get some crayons, some markers, or something like that, and just draw in where it should be power, where it should be ground. That's essentially what I did here, and now I'm going to try to figure out what could cause the problem. This light works, which tells me everything to right there is good. You want to do as much of your diagnosing from the wiring diagram as possible. It'll save you all kinds of time on the car. The other thing is the low beam lights work, which tells me most likely the ground is good. Now, the high beam and the low beam do have 2 different grounds. However, both these low beams don't work. And is it likely that both grounds went bad at the same time? Obviously no. Careful of that, because there was a time a customer brought the car in to me and they said, both remotes don't work. Well, if both remotes go at the same time, it's not going to be the remote, it's going to be the receiver in the car. Check the receiver had power and ground, and that was the end of your diagnosis. Spent $100 and some, put a new receiver in there, and I couldn't program it. Went back and talked to him, and he goes, oh yeah, the one quit working a year ago. So like, okay, that would have been good to know before I started. That it would have been possible that both the high beam lights were out, but we're going to assume that I've checked that already. The other thing I know, both lights don't work. I'm going to guess that the problem is before this area here, because if it was this wire that was broken, it would only be the left-hand light that didn't work, the right hand still would. Just by looking at the wiring diagram, I can narrow down that my problem is most likely going to be right inside of here. From inside of here, I've got this splice, so the splice actually could be bad. I have this connector 150 right here, and I have this grommet, which they call P100 for pass-through grommet, to a splice out here. The headlight switch. Don't know what the vehicle is, so this could be on the dash or on the steering column. Dimmer switch, definitely on the steering column, so I know this connector is going to be right at the base of the steering column. I'm familiar enough working on cars. This P100, I know that is where the wires go through the firewall. Everything before this is under the dash. Everything under this is under the hood. Where do I start my diagnosis? Other than I did start it with the wiring diagram. You will have people tell you when you start your diagnosis, start in the middle of the circuit. Because then if you come to that midpoint, if the voltage is what it should be, everything is good up to that point. The problem has to be after there. So you did half of your diagnosis with your first test. I'm not going to do that. And the reason I don't do that is while I'm teaching students how to do this, we'll look at a wiring diagram and I'll say, okay, where should you start this? And they pick that midpoint. And I say, okay, that switch that's in the center console, it's going to take you half hour to pull the center console apart, do your test, and put it back together. And it's like, oh, okay, you don't really want to. So we follow through and find, hey, this wire comes up behind the driver's seat. And that one, just move the driver's seat forward. There's your connector. Find the easiest place on the car to get to. If we look at this car, this P100 is almost always a pain to get to because they've got it buried. But the C150, it's up underneath the dash. It's relatively easy to get to. The only thing I have to pull down is a hush panel to be able to get to that. Get to my C150, check it to see if it has 12 volts. If it does, I know the problem is after this. If it does not, it's either going to be the C150 itself, and normally if it was, you would see it, it'd be a burned connection, or it's going to be that splice, and I have to go and find that splice. If I do have battery voltage there, next place I'm going to go is this splice that's out under the hood, just because I know that P100 is a pain to get to. While you're diagnosing, find the easiest place to get to, start your diagnosis. And on this one here, where we're talking about lights that don't work, I know that I'm looking for either an open or for really high resistance, such as the burned connector. A short internal, that's going to cause a fuse to blow. Or in this case, it has the circuit breaker. It would have caused it to be turning on and off. If I had a short to ground, same thing, that circuit breaker would have been popping on and off. If I had a short to power, well, it would have meant the light stayed on, it wouldn't shut off. While you're filling out a repair order, and when you're diagnosing, don't just write down a short. Now, if you're a student in my class, I give you a scenario of an electrical problem, and you tell me, oh, it's shorted. You just missed the question. If you're working in a shop, you want to make sure that you fill out the information in detail. So, for example, I was working on a Suburban that came in for a 90K service, and on the 90K service, he didn't even complain about it, but there was a code for the O2 sensor. I don't know why, but for some reason I went and looked at the history, and that O2 sensor had already been replaced 3 times. Now I'd be putting on a 4th O2 sensor. Went and talked to the service writer, said, look, there's got to be some other problem on here. They gave me an hour extra time, so I went through and started tracing. What I found was there's an L bracket, so a metal bracket that's shaped like this, and the wiring loom is supposed to sit inside here, but when somebody put it together, that L bracket went up inside of the wiring loom and had cut through some of the wires, repaired the wire at that spot there. On the repair order, I filled out bank 1, sensor 1, O2 sensor signal wire, the wire color, the circuit number, and where I made the repair. If I put on there, repaired O2 sensor wire under the hood, the person goes down the road, 5,000 miles later, their check engine light comes on, they go to another shop, and this next shop repairs another wire that I've missed. So they repair an O2 sensor wire under the hood. And this guy's thinking, okay, I just lost a day of vacation, I had to stay in a motel an extra day, and they had to do a repair that this last shop said that they did. So they take the shop to court. And the judge, who's not technical, is going to look at O2 sensor wire repaired under the hood for mine, O2 sensor wire repaired under the hood for his. Well, there's 1602 sensor wires with 4 different sensors. It would have been a different wire, but to a non-technical judge, they're going to look at it and say, yep, that I was in the wrong, my repair didn't work right, so they're going to make the shop pay for everything. Found open wire, found wire shorted to ground at this spot, and circuit number, wire color, whatever. Put as much description in there as you can. So I hope you found that helpful, and that ends this video.